Hello everyone, greetings to all. My name is Keshav Pandey and I am from Material Science and Energy Storage Laboratory, Department of Physics, Daegu University. First of all, I would like to thank for giving me opportunity to present my research work on the topic modification of tungsten disulfide for electrochemical energy storage and conversion for ANPA and that local organized committee Nepal Physical Society. And I would like to present first what is the scope of our work, why we are using this research work to modification of the materials for energy storage and conversion part. So we have used this plasma treatment to modify physical and chemical structure of the top layer. On the top layer, changes surface habitability, polarity change and functionalizations. Also it can help for increment of active sites, electrical conductivity, surface area and hydrophilicity. Also we can change some phases of the materials from 2H, 2 hexagonal phase, that is semi metallic, to 1T phase, that is metallic phase, that could help for increase the conductivity by forming cracks on the surface and creating S vacancies on the surface of the edge of the materials. And this is our schematic what we have used in our lab. This is the plasma treatment devices, and this there is one needle, that is positive electrode that acts as positive electrode, covax needle, and bottom one there is you can see here is a yellow color, there is copper tape. This copper tape act as negative electrode. This positive electrode and negative electrode we have connected to high power supply, and these are the samples. This is solution samples. This WS2 is before plasma treatment, and this PWS2 means after plasma treatment. So from this using these applications we have research on the materials 2S2, tungsten disulfide 2S2, in the conversion part HER OER catalytic activity, and energy storage part there is flexible supercapacitor device. And I am going to present in the next slide how it works, experimental procedures. And first one is this first one is our plasma devices in our lab. I have already shown in the schematic one, and this is how this plasma how this works, this plasma treatment on the surface of the materials. And this is before plasma treatment, the surface sample is like this one, and after plasma treatment there is some increment of some habitability and hydrophilicity. And some experimental procedure we have used 300 milligram WS2 plus 30 ml water, and vacuum filtration, and dried in a 60 degrees Celsius. And after plasma treatment we have prepared 4 samples before plasma treatment, 30-minute plasma treatment, 60-minute plasma treatment, and 120-minute plasma treatments. After 120-minute plasma treatment, the solution is evaporated like dehydrated, and finally sample shows this lining structure by plasma treatment by the needle of this plasma treatment devices. And I'd like to go in the next slide in electrochemical measurement in 3 electrode systems. And this is first one is current voltage curve, CV curve. We can see there is some area of the integrated curve is higher in case of P2WS2. P2WS2 is considered for this WS2 is P1WS2 is 30-minute plasma treatment, P2WS2 60-minute plasma treatment, and P3WS2 is 120-minute plasma treatment. From this CV curve we can see we can calculate specific capacitance using this formula. A is integrated curve, M is mass loaded on the electrode, delta V means this potential window, and the small this new B is this is scan rate. We have used here 100 millivolt per second, but in all scan rates P2WS2 shows highest capacitance. And this in figure number C we can see that there is a charge versus time. This is used for calculate the electrochemical active surface area. From this Anson equation you can see there is this from A we can calculate this is Q and this is time T, and the electrochemical surface area is higher in case of P2WS2. And another similarly we also investigated to measure the impedance behavior of our this modification materials. This in case of this in figure of D we can see P2WS2 have smaller this internal resistance, and this semicircle part is charge transfer resistance is very small compared with another samples. This line is diffusion coefficient with this Warburg constant. This is the Rendell equivalent circuits. And another part there is surface morphology and structural characterization. This is these are the same images, and these are the TEM images, and these are WS2 for before plasma treatment, and P2WS2 is after plasma treatment. And we can see comparing with this two before plasma treatment there is some bulky shape, and there is very like this layer structure. But after plasma treatment, on the edge side there is some modification, some cracks on the surface of the material. So this is the modification of after 60-minute plasma treatment. This also SRTM, you can see that there is an interlayer distance of 0.61 nanometer, and in case of P2W2, 0.66 nanometer, means interlayer distance is increased after plasma treatment. And from SAD pattern, there is polycrystalline type pattern. This is more amorphous one, and this P2WS2 is another a little different morphology, different diffraction pattern compared with before plasma treatment. There is two hexagonal shape in 1T, another in 1T phase we can see that 2S and mix of 1T. 1T is little bit, the distance is increasing in SAD pattern. And another character, we have characterization of the samples using XRD and Raman also. From XRD and Raman, the peaks are well indexed on this, but there is different between 2H. This is 2H hexagonal shape, but there is additional peaks we can see here. This in the form asterisk, this red color. This is the additional peak from this 2 hexagonal type. Then this one, this is the difference with this is the characteristics of 1T phase. And in Raman also, J1 and J2 are additional peak. These are the 2H phase, and this J1 and J2 are additional peaks for 1T phase. In this figure number C is the bed surface area measurement, nitrogen adjustment, displacement isotherms. We can see that WS2 and PS2, comparing these two, P2WS2 have higher surface area, and the surface area is for WS2 7.2 and P2WS2 30.6 meter square per gram. And in case of this pore side distribution also, there is more volume occupied by P2WS2 and the size is 3.94 nanometers. The size is decreased after plasma treatment. And this is the X-ray photon electroscope, X-ray photon spectroscopy measurement, XPS measurement. And from XPS we have detected four main peaks: W4F, S2P, C1S and ONS. In W4F and S2P you can see that this red color shows the 1T WS2, and 2S shows 2 hexagonal type 2S phase. And in WS2 only 2S phase is occurred, and in after plasma treatment there is additional peak occurs with the red color, that is the 1T phase. And from XPS measurement we can summarize the elemental distribution W, S and O. From this this histogram, the P2WS2 have little bit oxygen increase because we have used Ambient solution plasma treatment on the surface of the samples. And this is the electrocatalytic performance of the samples. This is the part of this this conversion part, energy conversion part in the form of hydrogen and oxygen gas. And this from electrocatalytic performance, this is the HER measurement. This first two figure are HER measurement, and this is the overpotential, shows a very low overpotential in case of P2WS2 around 119 and 190 millivolt, and the table slope is 113 millivolt per DEC. And we have also compared with PTC. This is comparing with the commercial one, PTC, and this is not bad. That is the very comparable results. And in case of OER measurement also, from OER we have compared with RuO2 also. In case of P2WS2 the overpotential is low than other samples P2WS2. And in this table slope of OER measurement, the table slope of P2WS2 is 124 millivolt per second. That compared with others, this is low value of tafel slope. And we have also checked for stability measurement is very important. So we have checked after 3000 cycles. After 3000 cycles, P2WS2 have little bit little variation. There is almost no variation. But in case of WS2 there is more. This variation means not stability compared with P2WS2. Also we have checked IT curve, this corner we call a corner amperometric curve. And this comparing with this one, this is for OER measurement and this is for HER measurement. Comparing with this one, P2WS2 have more stability that compare with WS2. And in also we have checked for charging discharging cycles for three electrode system. And this is the schematic of 3 electrode system we have used for spin coating on the, this is the nickel, the substrate is nickel from substrate. And we have checked this CV curve little bit oxidation because we have used plasma treatment with solution plasma treatment. So in case of comparing with this discharge curve, the P2WS2 have this discharging time is high, so it can give more capacitance performance. And from this DCPL we have calculated from specific capacitance, and the specific capacitance is higher in case of P2WS2. And also I would like to more discussion in the next this two electrode system. And in two electrode system, uh, the P2WS2 device shows a very this good CV curve. This integrated area is more. Also we have checked for stability by bending. This is we have used P2WS2 as a positive in and negative in have the same material, so it is called symmetric supercapacitor device. And also we have checked for flexibility from 0, 45, 90 and 180 degree. It shows almost same CV curve. And at one and current density, after comparing, the P2WS2 have more discharge curve, and from this discharge curve I have put here some formula: I into delta T upon M into delta B. I means I by M is current density, delta T is a discharge time, and delta V is this potential window 0 up to from 0 to 0.8. And after calculating specific capacitance, there is 157.4 Fj minus 1 we have got. And from power density and energy density, 40 WSK per kg, and power density is around 400. And in case of capacitor retention and cooling efficiency, we have got in P2WS2 89.5 and 76.9 this 89.5 and 70.8 for this one. But in case of this P2WS2, 94 and 89.5 for P2WS2. And I would like to summarize and conclusion part. The tungsten disulfide is modified by using ambient solution plasma, and in case of HER and OER, this low potential 190 millivolt, and for OER case 0.21 volt. And there is stabilizer 130 millivolt per DAC, 124 millivolt per DAC, and capacitance of 157.5 Faraday per gram at 1 current density, 14 inner density of 14, and power density of 400. For the flexible super capacitor is obtained. Specific capacitor 94%, and Coulomb efficiency Coulomb efficiency of 89.5% after 5000 cycles are also demonstrated. And finally we have electrical high active surface area in case of P2WS2 after 60-minute plasma treatment, lower impedance, and the phase transformation also changed from 2S to 1T compared with WS2. That is good and could be applied for HER, OER, and supercapacitor performance. Thank you for your attention. Please any questions, and thank you again.